Have you ever really thought about what it means to measure something perfectly? To find its one single true value? We kind of take it for granted. But what if it's just not possible? What if this whole chase for the perfect measurement is just an illusion? Let's dig into why the right answer might not be a point, but a space. So let's just ask it straight up. How precise can we actually be? Is a perfect measurement even a thing? Or are we all just chasing a ghost? Honestly, the answer to that question could totally change how you see the world. At the heart of all this is a clash between two big ideas. First, you've got the point image. This is the ideal we're always chasing. It's that single true value, the perfect bullseye on the dartboard. But then there's reality, and reality gives us the interval image. This is a range, a space that embraces uncertainty. It's not the tiny bullseye itself, but the entire scoring ring where our measurement could actually land. Okay, so if that perfect little point is a fantasy, how do we get anything precise? Well, the answer is to stop fighting it and start embracing the interval. And look, this isn't some kind of compromise. It's actually a more honest and, frankly, a much more powerful way to understand what measurement is all about. So let's lock in a definition here. The interval image is what numerical analysis is really about. It's not about pretending we can hit some infinitely small theoretical point. No, it's about honestly defining the boundaries of what we know and taking every bit of potential uncertainty and error into account. That is what real precision looks like. And, this isn't some crazy new idea. In fact, there's a great line that describes the interval image as the dramatis persona of measurement. Basically, the main character in the play. The point image, that's just the painted backdrop. The interval? Well, that's where all the real action happens. But why is this shift in thinking so important? Why can't we just try harder, build a better ruler and find that perfect point? The reason goes deep. It's woven into the very nature of reality itself. We live in a world filled with something called the entropy of experience. It sounds kind of fancy, but think about it. Our world is a constant, chaotic flood of information, of tiny variations and random noise. From the slight tremor in your hand to the temperature fluctuating in the room, the world is just plain messy. And it's that built-in chaos that makes pinning down one single, perfect point value pretty much impossible. So how do we even begin to conquer all this chaos? Well, it's kind of like a three-step process. You have to start right in the middle of that mess, in the entropy of experience. From there, you use abstraction as a tool to pull some order out of all that noise. And that lets you get to the final step, achieving a measure of fullness, which is just a cool way of saying a useful, truly precise understanding, which you get by defining an interval that captures the value you're looking for. Now, if you're still a little skeptical that point-based logic can let us down, let me introduce you to this really cool, kind of mind-bending thought experiment. It's called Poincaré's paradox, and it is a fantastic example of why our real-world perception doesn't always play by the neat and tidy rules of classical logic. Okay, let's walk through this step by step. First premise. Imagine you have two objects. Let's call them A and B. They are so incredibly similar in color, weight, whatever, that your senses just can't tell them apart. To you, A looks exactly like B. Simple enough, right? All right, now for the next rung on the ladder. You take object B and you compare it to a new object, C. And just like before, they're so alike you can't perceive any difference at all. So as far as our eyes can tell, A equals B and B equals C. So here it is, the million-dollar question. If your senses can't tell A from B, and they can't tell B from C, does it logically follow that you shouldn't be able to tell A from C? I mean, classical textbook logic would scream, yes, of course it does. But here's the twist. In the real world, the answer is often nope. You might be able to put A and C side by side and clearly see a difference. Each individual step was just too small to notice. It was below your perception threshold. But those tiny, unnoticeable differences, they add up. And that is Poincaré's paradox. It's a perfect real-world example of how the simple logic of equals can just fall apart when you're dealing with the fuzziness of actual human experience. And this paradox, it wasn't just some fun brain teaser. It was a big deal. It exposed this fundamental gap between clean theoretical logic and our messy empirical reality. It basically forced thinkers to develop a whole new kind of logic, one that was actually designed for the world we live in.
What this shows is a fundamental difference in how we think about the world. Classical logic is built on these perfect, discrete, true or false states, where equality is absolute. But this new logic of indiscernibilities, it's based on what we can actually perceive. It accepts that A seeming like B and B seeming like C doesn't guarantee A will seem like C. In this world, truth isn't some single point. It's an interval truth. And equality isn't a perfect match. It's about being close enough.
And this whole philosophical shift led to some incredibly powerful practical tools. It gave us things like interval semantics, which is a way of defining meaning inside a range, not just at a point. It created the formal logic of indiscernibilities, a real framework for handling vague concepts. And maybe most importantly, it led to interval arithmetic, a whole new type of math, a calculus of intervals designed to compute with uncertainty built right in. This allows us to do calculations with ranges instead of just single fragile numbers. So this all leaves us with a pretty fascinating question to chew on. If a perfect point is a myth, what does it even mean to be right about anything? Maybe being right isn't about hitting some impossible microscopic target. Maybe it's about honestly defining the boundaries of our own knowledge, embracing that uncertainty, and finding precision within the interval. Now that's an idea worth thinking about.